Okay, so sorry, started the movie late, as if anyone's going to watch it. Actually, fifth and sixth hour have to watch it. Poor them. They don't get happy Mr. Stamulus today. I gotta leave. I gotta go to this thing, some sort of thing that makes me a better teacher or something. I don't know. Doubt it'll work. But sine 3740 over 176, and all that long, unbearable time. Did anyone get the answer? That me sitting here waiting? Nobody. Now one person first hour. I'm sorry, someone did. What'd you get for X? 282 what? Point 0.6. And then what do we put on that? Pounds of force. Okay, so that's the resultant. Okay, then, and you didn't get to see my exciting finding all these angle measures from what's given, but hopefully you can figure out it's really basic geometry. And then for y is opposite 4110 through all that, angle description. So this one is, anyone have this answer already? Because I knew how to do it. Sine of 4110 opposite y, the second force. I'm going to stick with the original sine of, this one, sine 3740 over 176. Hate when that happens. This angle measure is smaller than this angle measure, so y should be a little bit bigger than 176. So it feels right to me. Okay? So anyway, resultant, two forces acting. Remember the rope example. Pull, pull, that's where the object flies. All right, so know how to make the drawing. All right, same thing. I think this is number 3. I think I assigned number 4. And actually, I did this in a stupid way. There I go again. I just called myself stupid again. Sorry. Ugly. All right. Because it's kind of silly what I did. I didn't give you a chance to read it, so go ahead and read it. But I did this sillily. Very silly. You can see I found 2 angles. I decided, okay, I guess the way to do this is to find this angle, and then this angle, and then do what with these 2 angles to find the angle between the 2 forces? Add them. But that's silliness. Because what do you know about this angle compared to this angle? What do you know about this angle compared to these 2 angles, or both that big angle? They're supplementary. So I should have just found this angle and then did what? 180 minus. So how would I find this angle? Through the what law? Law of cosines. So you feel free to write this down. I'll show you the other way where I doubled my work. All right? So it's cosine of this circle, I don't know, I couldn't think of a symbol, equals this squared plus this squared minus this squared over 2 times this. Inverse cosine, get your answer, 180 minus. Or use the law of cosines twice. And then do what with those 2 angle measures? Add them up. Okay? Simple Simon. Ain't no thing, chicken wings, and all that other stuff I say. So this is kind of silly, and I yanked the example right out of the book, but just to get you to understand this is really not much different than the last example. And I don't know why they make a big deal out of this, but it's really not a big deal if you just follow along. So what's an equilibrant? It's an equal opposite force that creates balance with the resultant. So here we have, again, 2 things pulling on an object. This is pulling this way at 48, what do we got, newtons. This is pulling this way at 60 newtons. This is the resultant. Well, an equilibrant would be an equal and opposite force that would keep this stationary, and there would be no movement. If we increase these forces over here, then we start winning this way to the right. If we increase the equilibrium, easier for me to say, then it'd start moving the other way. So, I don't know. I know it's weird, but it's just, this is what it is, and just deal with it. Good morning. Okay, so find a magnitude of the equilibrance of the forces. of 48 and 60. All that means is find the resultant, the equilibrant is equal to that. But then where it gets tricky is then find the angle between the equilibrant and the 48 Newton side. So again, if this isn't drawn, you have to create this drawing. Okay, fine. We have two forces acting on an object. We draw our parallelogram. And then just after you draw the resultant, draw the equilibrant going in the opposite direction. Try to make it the same length, looking like it's the same length. So the resultant's magnitude is equal to the equilibrant's magnitude. Just going in the opposite direction. You don't have to put a negative on that. It's just, it's 98 newtons going the other way. By the way, we got the answer. I found it. Actually, I just cut out what the book said. It's right here. You would know to find that equilibrant, all I would do is, and what did I say here? The force between them is 50. So that yet again, if this is 50, then I use 130 because 130 is opposite the resultant. The mistake that I covered about number 55 in section 7.4 that 90% of us made. So you can see the law of cosines with 130 in there, and then you get 98 newtons for the resultant. So if the resultant is 98 newtons, then so is the equilibrant. Not a big deal. Because they asked me to, I have to find that yellow highlighted alpha that I have right there. Why then do I have this angle marked here? That's interesting. Same person again, good. They're supplements. So if I find the blue highlighted angle, to find the yellow one, all I would have to do is do what? 180 minus. So now that I have this 98 newtons, and it's probably been smart to not round on this, but I'll just use 98 newtons. Now I could use what? What could I use to find this blue angle measure? Law of sines. So then you use the law of sines to find theta, and then 180 minus that answer. And then what that does is at least it gives a direction for the resultant in relation to all of the parts. And that's why we would find that if we wanted to figure out some more stuff about this thing. Sorry, I should have taped that, but we're talking about, all right, second type of things we're going to do. And actually, it's the last one of the day. So that's why I'm kind of taking a long time, but that's fine. For you physics people and everyone else, you will be graded 2 points for completing the correct drawing with the angles in the right spot. I couldn't care less that you know the formula, if you do know it. Well, after I do this, you probably remember. Okay, so here's what's going on. And I'll give you a second to write if you want, specific notes, writing the word problem down and then getting the drawing. I'll explain the. Okay, so here's what's happening. Gave you a chance to write the question down. Now I'm going to zoom in this drawing and get you to understand all the components of this, and then we can derive what people in physics may recognize as the formula they know in order to do this. So, of course, what we said was the angle of the ramp matters. The more of an incline, the harder it is to pull this wagon. We'll assume, even though it's not true, that these wheels are the best wheels ever in the history of the world, so there's 0 what? Friction. There's also a friction thing in here. There is still some friction in the wheels, but we're going to pretend it's friction 0. All right, and so there's a couple things going on. First thing is, this is the force vector. Is this working here? Where's it? Oh, there it is. Okay. Force vector right here. This is the force needed in order to pull the wagon up the ramp. But I think what they have here is required to keep this from sliding down. So actually keep it in a state of equilibrium. But that's not the same as the last one. Basically what we want to know is how much force do I need to keep it from moving? Then if I increase that force, it'll go up. If I decrease it, it'll go down. So what's the state? That's perfect for keeping this from moving, and then I just have to increase it to get it up the ramp. Blah, 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 blah. So this is the force to pull it up. Well, again, what's affecting this scenario? The first thing that everyone's affected by daily is what? Gravity. That's this vector right here. That's the one vertically. Gravity is hitting us right in the head. And how is gravity expressed on Earth? And actually anywhere, what we like to express gravity in terms of pounds. All right, so this wagon was 50 pounds. That's a force vector. And that's the one vertical to, perpendicular, wrong word, to if this was flat ground. So the first thing you'll need to do is put a 90-degree angle right here with that gravity vector. Well, then the next vector is this one. How do you explain this vector right here? What's that vector represent? Well, that's the vector that is affected by how much incline is in the ramp. It is the vertical, I did it again, the perpendicular to the ramp. All right, and you can see if this ramp was more slanted, then this vector would change. So this is a vector that incorporates the effect of the ramp's incline. And it is the perpendicular to that. So you must draw that and put a 90-degree angle right here. So now remember, the only thing that was given is the ramp is 20 degrees incline. Well, now it's simple geometry. Watch how this all shakes out. And yes, you do flash this all the way down here, and then you create what is really a parallelogram again, because then this force vector is the same as this force vector down here. We're going to need that to kind of derive the formula. So in a way, it is very similar to what we did with the resultant questions, but it's a little bit different. Okay, so this force vector, if I complete this parallelogram, is equal to this, and then I'll get this as a label or I'll be able to find it. Okay, now it's simple geometry. How did I get 70 here? It wasn't listed in the question. How did I get that? 180 minus 90 and 20. That's 70. How then is this 20 right here? Well, what's this whole angle measure from here to here? What is all of that? All of that right there. 180. Well, I already have 90 and I already have 70. So what do I have left over? 20. So, in these questions, if you draw this correctly, the ramp's incline will always be this angle measure as well right here. Okay? Now, the weight of this object is 50 here, and now I know that force is over here. Tell me how I'd be able to find this force then. What simple trig function could I use knowing that 20 is there and F is across from that? And this is the what of this triangle. Hypotenuse and opposite. You're killing me, Smalls. What is it? Sine. So it's sine of the incline degree measure equals the force divided by the weight. And that's a 50. That's a fancy 5 now. So then really all I have to do is multiply both sides by 50. Look at how easy the math is to do this question. You must have the drawing and you must have the right angles in the right spots and then this right triangle drawn correctly. Biggest mistake people make is putting the right angle right here. Happens like 50% of the time. So just make sure you understand how this all shakes out so we can get that drawing. Hey, by the way, what's the force? 17 what? 0.1? How do I label that? Pounds. Because this is in terms of weight and pounds of force and so on and so forth. Dog. One more. What? What happened? There's a controversy. Required to keep a 3,000-pound car parked on a hill that makes an angle of 15 degrees with a horizontal. This reminds me of another story. Remember one yesterday? My cousins lived on a hill in Orland Park, and one of my cousins there, he said, "Hey, let's go in the car and shoot spit wads at other cars as they go by." So we did, and went in my mom and dad's car. And back in the day, these old cars, you could mess with the gears without having the keys in. So my cousin was in the driver's seat, and I was in the passenger. And as we're doing this, two little punks, he goes, "Hey, do you dare me to put the car in neutral?" No, I did that. So not knowing that I didn't, and I wanted to scare him a little bit because I was a little older than him, not knowing cars real well, I put my foot on the gas, not the brake. Now the car wasn't, on. So I put it in neutral. Of course, my foot's not on the brake, it's on the gas. So what does the car start doing? Starts rolling. So I panic. So what do? I don't move my foot to the brake. I keep pumping the gas. It's rolling. I go, Cuz is already out the door. He left. I'm like, oh no, it is rolling faster and faster. So it somehow it turns, just misses a car. I jump out that same door. I crossed the side that he went, jumped out. The door hit a car, door slammed, and then the car ended up hitting the house at the bottom of the hill. True story. Isn't that horrible? I'm like a little punk, aren't I? I get a lot of bad stories. True story. Oh, they were mad. It was bad. That was one of my worst things I've ever done in my life. Anyway, so here's the car parked on a hill, and the hill has a 15-degree incline. All right? And then, all right, so here we go. This is how you draw it. And I didn't want to do that other one before because it had the drawing for you already. And that's all I want to do. The car's somewhere up here. I could draw it, I guess, but I won't. Okay, so now, do some colors. First things first, this is the what vector. What vector is that? If it's a right angle with this, what is that? Okay, it's perpendicular with the ground, so it is the what? Gravity, but that is also described in what? What? Weight. No one said it. Right, this is 3,000 pounds, correct? Okay, then we need to draw this vector. I'm trying to pick a color here. The perpendicular with the ramp. Okay, so I need to draw that one. That incorporates how the ramp affects this situation. Well, actually, in this case, the hill. So we do a perpendicular with this hill, and that's how the ramp affect or the hill affects this. The more degrees, the more force we're going to need to keep this from moving. Then we need this one. This is, and it's actually a little bit too long. This is the force needed to keep this car stationary. All right, pulling straight up the hill like this, which is the same as this. This is the force needed to keep this from moving. Okay, so know how to draw it, and that's why I kind of went over this real fast. All right, and then after all of this, okay, I forget. I don't know where that angle measure is. Well, if this is 90 and this is 15, what's left over for this angle right here? 75. If this is 75 and this is 90, what's left over for this little sliver? Right back to 15. Okay, so again, it's the same thing. How do I get this force? And by the way, this is where the right angle is. Right here, because these are alternate interior angles. Probably didn't say that in the last question. It's sine of 15 degrees equals F over 3,000. And then 3,000 sine 15 is the answer. Just for giggles, what's 3,000 sine 15? Someone help a fella out. 776 what? 0.5 pounds of force. So if I was that punk again up at the top of the hill and I put this in, did the same thing I did back when I was a kid. That's a terrible car, by the way. Someone could grab the fender and hold it from going down the hill if they were that strong. Right?